Hello, in this video we're going to go over the relation between row operations, matrix multiplications, and determinants. And in this video we're going to prove one of the most important properties of determinants, which is called multiplicativity, which means determinant of AB is equal to determinant of A, determinant of B. Before we get to that, let me start with some examples. So let's say you're doing some row operations. There are three row operations that we have talked about: row interchange. So let's assume you have a matrix with three rows and you're swapping the first and third row. So I'm going to replace the first row by the third row and the third row by the first row and not change the second row. So this row swapping corresponds to a matrix multiplication. So in order to bring the third row to the first row, I will have to multiply the first row by, and let me write it down on this side, in fact, because I want to write down the swapping the rows in terms of the original matrix. So this is the original matrix, and this is the matrix that I obtained after swapping the first row and the third row. So I would like to bring the third row to the first row. So I will have to multiply the first row by 0, the second row by 0, and the third row by 1. If I do that, when I multiply this one by this one, I will get 0a1, 0a2, and 1a3. So a3 comes to the first row. I want to not change the second row, so I'll have to multiply the first row by 0, second row by 1, and the third row by 0. And finally, I want to bring the first row to the last row. So I will have to multiply the first row by 1 and then 0, 0. So this matrix is a matrix that is obtained by swapping the first row and the second row of the identity matrix. So this is almost identity, with the exception that first and third rows are interchanged. So that's how we obtain that matrix. Now that is the first operation, row swaps. Now look at row addition. So if I look at again matrix A1, A2, A3, let's say I add a multiple of the third row to the second row. So A2 plus C, A3, and I don't change the other two rows. So I'm not changing the first row. It means I have to multiply it by 1, 0, 0, so that keeps the first row intact. I'm adding this C times the third row to the second row. So that's how we can add C times the third row to the second row, and I'm not changing the third row. So this is a matrix that is again almost identity with one entry that is changed. One entry has changed from 0 to C. This is the matrix for row interchange, row addition, or row replacement. The next one is a scalar multiple. So if I do A1 and then I multiply the second row by C and I keep the third row, this is like multiplying A1, A2, A3 by 1, 0, 0. That doesn't change the first row. 0, C0, that replaces the second row by C times the second row, and the last row becomes 0, 0, 1. And this is also again called this is also another matrix that is very similar to the identity matrix. These three matrices are called elementary matrices. So what is an elementary matrix? There are three types of elementary matrices. So each one of these is called an elementary matrix. So what are the elementary matrices? I have them listed here. The outcome of each row operation to a matrix A is a matrix E times A as follows. If the row operation is interchanging the ith and the jth rows, then your matrix E is of this form. So this is identity, except that the ith and jth row of the identity matrix are swapped. This is one type of elementary matrix. The second type corresponds to row scaling. If the operation is scaling the ith row by a factor of c, then E is E1 through En, except that the ith row must be multiplied by c. So again, this is almost an identity matrix with one change, with the ith row multiplied by c. If the operation is row addition, adding a multiple of the jth row to the ith row, and of course in this case I and j are distinct, then you would get E1 through En, and the ith row is Ei plus c ej, and I and j are not the same. These three matrices, matrix of row swapping, row interchange, matrix of row scaling, or matrix of row addition or row replacement, these three are called elementary matrices. These play a significant role in our next theorem. Okay, so let A and B be two matrices, n by n matrices, then determinant of AB is the same as determinant of A times determinant of B. This is a very important theorem in linear algebra, in properties of determinants. So we are going to use elementary matrices. Before I can use elementary matrices, I'm going to start with the case where the rows of A are linearly dependent. So suppose rows of A are linearly dependent. So what does it mean? It means if I take A to be A1 through AN, then we know C1A1 all the way to CNAN is 0 for some scalars Cn in R not all 0. So what does that mean? It means if I look at the vector C1 through Cn and I multiply that by A1 through AN, then I'm going to get C1A1 all the way to CNAN. And what is C1A1 all the way to CNAN? That's exactly 0. So, and this is exactly A. So what does that mean? It means if I multiply C1 through Cn to A, I get 0. Now multiply both sides of this by B from the right. You would get C1 through Cn times AB equals the 0 matrix. What does that mean? And in fact, it's the 0 vector, but it is also a matrix. Now, what does it mean? It means if rows of AB are, let's say, B1 through Bn, if AB is equal to B1 through Bn, then I would have C1 B1 all the way to Cn Bn equals 0. And what does this mean? It means rows of AB are linearly dependent. Okay, so this was the case where rows of A are linearly dependent. So I showed that rows of AB are also linearly dependent. So by a theorem, we have shown this one in the previous video, determinant of A and determinant of AB are both 0. And what does that mean? It means in fact determinant of AB is equal to determinant of A times determinant of B. This is the case where rows of A are linearly dependent. Now assume that, so this was like basically two cases that I took. The first case was where rows of A are linearly dependent, and the second case is where rows of A are linearly independent. So assume rows of A are linearly independent. So because of that, we know that the reduced echelon form would have to have one non-zero entry in every single row. It's a square matrix. So the reduced echelon form must have n pivot entries. Now, since A is n by n, there's only one reduced echelon form, and it will have to be the identity matrix. The reduced echelon form must be the identity matrix. Okay, so now let's see what happens. We just talked about how row reduction is the same as multiplying by elementary matrices from the left. So what we get is this. So after we take A, we apply a row operation, and we will get to E1A. We apply another row operation, we get E2E1A. And eventually we get to this is equal to identity. So we know that. Now let's see what happens when you multiply a matrix by an elementary matrix. So now let E be an elementary matrix. So what is the product of an elementary matrix and A? We talked about that earlier in this video. So if you look at E, there are three possibilities. The first possibility is E is a row interchange matrix. If it's a row interchange matrix, then determinant of E is going to be, when you change two of its rows, you're going to get determinant of identity. So it will be minus determinant of the identity matrix, which is minus 1. What is determinant of EA? Determinant of EA, because we are swapping two rows, is exactly the negative determinant of A. So what does this mean? It means determinant of EA is exactly determinant of E times determinant of A. That is if E is a row interchange matrix. Now, what if E is a row addition matrix? So this is the second case. So what is determinant of a row addition? Determinant of E, you can just do another row addition to get it to identity. So that becomes exactly determinant of identity, which is 1. But we also know that determinant of EA and determinant of A are the same, because row addition doesn't change determinant. Determinant of E times determinant of A, because determinant of E is exactly just 1. So what does it mean? It means for these two elementary matrices, we do have determinant of EA equals determinant of E times determinant of A. The last case is E is a row scaling matrix. Then we have a C on the diagonal. So determinant of E is C determinant of I, which is C. But what is determinant of EA? Because we are multiplying the ith row by C by multilinearity, determinant of EA is exactly C times determinant of A, which is what we want, which is determinant of E times determinant of A. What does it mean? It means for all elementary matrices, we do have the multiplicativity. We do have determinant of EA equals determinant of E times determinant of A. Now back to the original problem. We got to this point. If I rewrite it, we got to this point. We got to EM all the way to E1A equals identity. Let's not take the determinant of both sides. We get determinant of EM all the way to E1A equals determinant of identity, which is 1. Now, because determinant of EA is determinant of E times determinant of A, I can take out those elementary matrices. So I can rewrite the determinant of EM times E1 all the way to E1 times A as determinant of EM times determinant of EM minus 1 all the way to E1A. So that is 1. We'll just do that again. We'll get determinant of EM, determinant of EM minus 1, and then again and again we get to determinant of E1, determinant of A equals 1. Now let's do the same thing but multiplied by B. This times AB is I times B, which is B. Take the determinant of both sides, we get determinant of EM E1 AB equals determinant of B. Now apply the same thing to this side, you get determinant of EM all the way to determinant of E1 times determinant of AB, just with repeating the same argument, equals determinant of B. But from the first equality that we had, this the equality that we got right here, product of determinants of E1 through EM is 1 over determinant of A. So we get 1 over determinant of A times determinant of AB is equal to determinant of B. So what does that mean? It means determinant of AB is equal to determinant of B times determinant of A, which is exactly what we wanted to show. This is a very important theorem in the study of determinants. So another application, one application of what we just talked about is that determinant of A and determinant of A transpose are the same. So let's prove this one. So we're going to apply a similar strategy for this one. There are two cases. The case one is rows of A are linearly dependent. So if rows of A are linearly dependent, then since A is a square matrix, its columns are also linearly dependent. And the reason is by counting the pivots, So it's pretty straightforward based on what we had seen before. The number of linearly independent rows is the same as the number of linearly independent columns. Therefore, if the rows are linearly dependent, the columns would also be linearly dependent because it's a square matrix. But in this case, determinant of A is 0 and determinant of A transpose is also 0. Why? Because rows of A are linearly dependent and rows of A transpose are also linearly dependent. So that's the case where rows are linearly dependent. Now let's assume that rows are linearly independent. So we're going to do a similar strategy. So rows of A are linearly independent. So by what we just talked about, EM all the way to E1 times A becomes identity for some elementary matrices. Okay, so we're going to take the determinant, so we get determinant of EM all the way to determinant of E1, determinant of A is equal to, and on the other side you get determinant of identity, which is just 1. We are going to take the transpose of both sides. EM all the way to E1A transpose is equal to identity transpose. Now transpose of product is product of transposes, except that they would be in reverse order. And this was an exercise in the later section. So you can write this down as A transpose E1 transpose all the way to EM transpose equals transpose of identity is just identity. So what I'm using here is XY transpose is equal to Y transpose X transpose. Not very difficult to see by looking at the entries of XY and also Y transpose X transpose. So now take the determinant of both sides. We get determinant of A transpose times determinant of E1 transpose all the way to determinant of EM transpose is equal to determinant of identity, which is 1. So if we show that this portion is the same as this portion, then determinant of A and determinant of A transpose would be the same. So we will have to show determinant of an elementary matrix is equal to its transpose. So if we look at, there's again 3 possibilities. E is a row interchange matrix. So if you swap the rows and columns, E transpose is also a row interchange matrix. So what does that mean? It means determinant of both of them are -1. So you can kind of see that pretty easily. So if you look at this one and you have, let's say you have a 1 here and a 1 here, and everywhere else is just the identity matrix. Then when you swap the first and second, when you look at the transpose of this one, you will get, when you look at the transpose of this one, you get the same thing. So it will be also swapping 2 rows. And it is always the case that if you have a row swap matrix, when you transpose it, you get also another row swap matrix. The next one is if E is a row scaling. In that case, E and E transpose are the same. So again, the determinants are the same. And the third case is if E is a row addition matrix. If you take a row addition matrix, again, the transpose would be another row addition. So E transpose is also a row addition matrix. Not very difficult to see. So what does that mean? It means determinant of E transpose is again determinant of E, and in fact both of them are 1. So for all elementary matrices, determinant of E and determinant of E transpose are the same. Therefore, these highlighted portions are the same. Therefore, determinant of A and determinant of A transpose must be the same. So thus, determinant of A, which is equal to 1 over determinant of E1 all the way to determinant of EM, is the same as 1 over determinant of E1 transpose all the way to determinant of EM transpose, which is determinant of A transpose. And that brings me to the end of this video. So next time we will continue with our talk about determinants and talk about some other ways of evaluating determinants. I will see you in the next video.